So now that we've already looked at molecules with different number of bonds, for instance, single, double, and triple bonds, I wanted to go ahead and show you this figure right here so that we can begin to kind of analyze and compare those different types of bonds. So this group of bonds, which I'm going to label A, this group that I'm going to label B, and this group right here that I'm going to label C, these are a little bit different from one another. What I want you to see are the similarities, but also the differences. And I want you to recognize some trends. So this first group right here for A, we've got carbon-carbon bonds. These are all carbon-carbon bonds. Talking about a single carbon-carbon bond, double bond between two carbons, and a triple bond between two carbons. Now, what's unique about this is if we look at our single bond, it has a length of approximately 154 picometers, whereas a triple bond is 120 picometers. Now, if you go down to this group B, we only have a single and a double bond. This is bonds between carbons and oxygens. A single bond is 143 picometers, whereas a double bond is 123 picometers. This last grouping, this group C, is carbon-nitrogen bonds. And if you look at a single carbon-nitrogen bond on down to a triple carbon-nitrogen bond, one of the things that you recognize across all of these is that your distance, your bond length, is going down. So as your number of bonds between two atoms increases, your bond length decreases. Now, there's an inverse relationship between bond length and bond energy. So bond energy, think about that as what is the energy that would be required to break that bond. So if we look at a single carbon-carbon bond, it takes 347 kilojoules per mole. If we look at a carbon-oxygen single bond, it's 358. A carbon-nitrogen single bond is 305. Okay, so those are all comparable to one another. But then once we get down to the triple bonds, or the highest order of bonds, so a carbon-carbon triple bond is 839 kilojoules per mole, whereas a carbon-nitrogen triple bond is 891 kilojoules per mole. So what we've seen there is as you increase the number of bonds, the bond energy, so the strength of that bond, becomes much, much greater. Now, in summary, what this shows is a table of a number of different molecules, comparing different compounds' bond strengths and bond lengths. So when we look at these three different compounds, we're looking at a single carbon-carbon bond, a double carbon-carbon bond, and a triple carbon-carbon bond. Now, this table, as it ultimately is produced, what I want you to see is that bond strength increasing. So as we go from a single to a double to a triple bond, our bond strength is going up and our bond length is going down. So the shorter the bond, well, the stronger the bond. That's a good kind of, yeah, shorter means stronger, longer means weaker. Now, triple bonds are shorter than double bonds, which are shorter than single bonds, which is not really much of a surprise, but that's another way of articulating what we already said in the previous slide. So a triple bond is going to be your shortest bond, and a single bond is going to be your longest bond. A triple bond is stronger than a double bond, which is stronger than a single bond. So your triple bond is your strongest, your single. So it's kind of easy to look at distinctions between if there are multiple bonds. But if we talk about an individual bond, specifically we talk about a single bond, is it fair to say that all single bonds are equivalent? We saw in the previous slide that a carbon-oxygen single bond, a carbon-carbon single bond, and a carbon-nitrogen single bond, those lengths and strengths were not equal to one another. So it's pretty safe to say that not all single bonds are equivalent. And ultimately, we have a little bit of a spectrum in which you could use to look at bonds. So you could compare a covalent bond to an ionic bond. And so think about those definitions. In an ionic bond, you are giving up. So electron not shared, like 100%. One atom has given up an electron for the other atom. In a covalent bond, a perfect covalent bond, as is indicated with something like H2, we've got 100% sharing. So you could almost look at it as a spectrum of, well, how much are those electrons being shared? We've got a covalent bond where it's 100%. On the opposite end of that spectrum is an ionic bond, in which case it's 0% shared. So we're going to get into that a little bit further, but keep that in mind for our discussion of bonds and kind of comparing them to one another. Thank you very much. Have a good afternoon.